So, first of all, I would like to thank the SWEMF committee because they kindly agreed to my doing this talk. I think it was a sort of parting gift as I stepped down as chair of SWEMF after 10 years. They let me indulge my two professions, as it were, of maths and music by doing this. So thanks very much for that. What I plan to do is to do a bit of physics, the physics of sound, a bit of revision, what I hope will be revision of maths, quite a lot of music, obviously, and then some questions. And I'm trying to think of a tactful way of saying this. I'm going to pitch this at people who don't remember very much maths. Now, I know there are lots of people here who know lots of maths, but I always used to say to my students, I would rather bore you than baffle you. In other words, it's better, I think, for people to be told things they already know than to have big gaps in their understanding. So if you're an accomplished mathematician, you can just go and drop off during those bits. And at the end, there will be a sort of postscript for mathematicians that might be a bit alarming for those who aren't. So try to keep a balance. Another disclaimer I must make right at the start, none of what I'm going to say has anything to do with pitch. I hope that wasn't a comment. Everything I say, and we'll see why, everything I say is true no matter what pitch we are at. So I am not going to enter into discussions about, whether it should be 3/9.
Claire, sorry to interrupt you. Sorry to interrupt you, but you've got a couple of people who are not muted, which is going to affect.
Ah, that's why we heard that noise. Yes,
affect the sound coming to the rest of us.
Thank you.
Even if they don't make any noises.
Can I mute everybody? I should be able to. I don't seem to be able to. Okay, if you're not muted, could you please mute yourself? Thanks, Steve. It is a bit distracting, isn't it? Oh, was I? Yes. So nothing to do with pitch. So, starting off with a bit of physics, what creates the notes of music that we hear is very simple. It's a repeating pattern of variations in air pressure. They hit our eardrum, they're transmitted to the brain, and again, anybody here who's a physiologist or a doctor, and I know there are some, will know more than I do about the mechanisms whereby that happens. But that is perceived as sound. So whether this vibrating object is the string of your viol, the string of your clavichord, or indeed your vocal folds, they all create vibration, and that is transmitted as sound. This helps to explain some of the terminology we use. So here is a graph of air pressure against time. A very bad graph because there are no units on the axes, but it's representational rather than specific. So we get waves of pressure going up and down in a regular pattern. This is the simplest sort of pattern. We'll see in a minute that there are others. That's, again, what we perceive as sound. So some bits of terminology. The period of a vibration is the time for one complete repetition of the pattern. So if I pop back to that diagram, the period of this one is the time for that oscillation, up and down. The term we more usually use, and this is where the famous 440 and 415 and so on come from, is the frequency of the sound. It's it's the reciprocal of the period, but it's easier to think of it as the number of complete repetitions, and we usually do it per second. So it's how many complete repetitions of the vibration we get in 1 second. And the amplitude is the maximum height or the maximum depth, not the whole width, but the height from 0 and the depth from 0. Now these determine very much what we hear. So the frequency tells us about the pitch, and I'll have a lot more to say about that in a minute. But basically, the higher the frequency, the higher the pitch of the note. So when we say A440, it means there are 440, why did I say that? Complete cycles per second. And the unit that's used for that is called a Hertz, after German physicist. So 440 complete cycles in a second. So it's a pretty clever trick, isn't it? When you sing an A, your vocal folds are generating vibrations at that speed. And if you're a soprano and you're doing an A an octave higher, then as we'll see, they're actually going 880 cycles per second. So I suppose I should have said for the note A above middle C in the normal concert pitch, or 415 otherwise. And the amplitude determines how loud the sound is. So the bigger the amplitude, the louder the volume, which is kind of intuitively clear, isn't it? Now, what I drew on my graph was effectively the representation of what we call a sine wave. And even if you're not mathematical, I guess you've probably heard that expression, or a sinusoidal curve. And it's what's associated with a pure kind of tone. You know, if you generate a sound electronically, the sort of basic sound is very straight, I would say, as a singer. It doesn't have any kind of character to it. So my first picture here is of that sort of note. Noise, on the other hand, is something which is completely random and disordered, and I suppose our poor old ears can't sort of, or our brains perhaps, can't organise that into anything perceptible as a particular pitch or a particular timbre, and so it just comes across as noise. It's random. A loud high-pitched note would have a high frequency, so lots of vibrations in a short time interval, and a big amplitude. Here's a soft high-pitched note, still lots of vibrations, but a much smaller amplitude. Here we've got a loud low-pitched note, fewer vibrations per second, and a soft low-pitched note. But those are all sine waves except for the noise. If you play an actual instrument, then you will get a very different sort of picture. You still get the repetitions, you still get the amplitude, but the actual shape of the plot, for want of a better word, it is quite different. So something which is very spiky will be perceived by the ear and the brain as a rather harsh sound, and this one, which is a triangular wave, will sound very unpleasant. For anybody who has had a child or had themselves the experience of learning in the early stages of playing a violin, you'd be interested to know that the sort of curve that you get from a not very nice violin tone looks very much like this. I think it's quite a good representation of what it sounds like. Now, there is a lovely toy on the internet called Online Tone Generator, which enables you to play around with this. And if I stop sharing this document and go here, then I should be able to show you how that works. So just to test, first of all, can everybody hear that note? Yep. So that's 440, and it's a sine wave. Down here, though, we can change the shape. So if we do a sawtooth, I won't say what that reminds me of. The thought of Renaissance winds never entered my head. A square wave energy, and a triangle, not too bad at all. So it's really quite a fun thing to play with. I should have said that I'm going to put, well, along with the recording on the website, I will also put a sort of handout with all these URLs and things that I refer to, in case anybody wants to go and have a further look. And I think one nice thing about this is that you can demonstrate. So I'll just do that one again as a sine wave. And that's a modern A. If I change that to 220, there's an audible demonstration of the fact that if we halve the frequency, we get the same note an octave lower. And if we do twice the frequency, we get an octave higher. So you don't have to take my word for it. There's a demonstration. Right, I will now revert to my slides. This is just a bit of an aside, but it's terminology that you may encounter if you read more around this. As I said, the unit we generally use is the hertz, which is the vibrations per second. But there is also a unit called a cent, which the name's a bit of a giveaway. It's 1/100th of the size of an equally tempered semitone. Now we'll talk about what exactly an equally tempered semitone is in a minute. But I mention it now because you may wonder just how small a difference in frequency your ears can actually detect. And it's been suggested that most people can distinguish differences of about 25 cents, which is a quarter of a semitone. So that's really quite a small interval. I think people are sometimes surprised that they can distinguish an interval of that size. But anybody who's ever played in an out-of-tune viol consort realises that very small differences can still be quite significant. And of course, people with what's sometimes called a trained ear can detect much smaller differences. If you want to test your pitch discrimination, I'm not going to demonstrate this now, but there's another nice website called the Music Lab, which has it's shown under the heading something like "Am I tone deaf?", which is a bit misleading. But it is actually a pitch discrimination test where you are played pairs of notes and asked to say whether the second one is higher or lower than the first one. And it's a piece of citizen science, because this comes from Harvard or Yale or somewhere, and they're collecting all this data from all the people who play with this thing to try and get a picture of how people's pitch discrimination ability varies. So that's another interesting one to play around with. And you can boost your ego by finding out that you're in the top 0.5% of the population in terms of your acuity or whatever. Right, so this is one of the bits where the mathematicians can go to sleep. But just to remind you, if you haven't thought about this stuff for a long time, that a ratio basically just tells you what fraction one amount is of another. So if we say the ratio of 12 to 15 is 12 over 15 or 4/5, that's the same thing as saying that 12 is 4/5 of 15. Not exactly a demanding concept. We use power notation to shortcut a series of multiplications. So 2 to the power 4 means 2 multiplied by itself 4 times. So 2 times 2 times 2 times 2, which of course is 16. So just a shorthand. And then conversely, if we want to undo that, we write 16 to the power 1/4, the reciprocal of 4, to show the number that, and this is a bit of a mouthful to say, the number which multiplied by itself 4 times gives 16. So 16 to the quarter, or another way of writing that would be the 4th root of 16 is 2. And there are going to be quite a few roots knocking around later on. So I hope everybody's happy with that. So as we saw from my audio demonstration, a note with twice the frequency of another note is perceived by the ear as being essentially the same note, and we give it the same name, so C, D, whatever, but it's an octave higher. Octave, of course, has something to do with 8, which we'll see in a minute. So the consequence of that is that it's not the absolute difference between the frequencies, it's their ratio that determines how two notes sound when we do them together. And this is back to what I said right at the beginning, that everything I'm saying is independent of the pitch. Intervals sound the same no matter what pitch we're at, and we know this. You know, a major third between C and D is the same whether you're playing down in the bass clef or somewhere up in the stratosphere. It's because it's the ratio that's the important thing. And a mathematician would say that that shows that intervals work on a multiplicative rather than an additive basis. So in other words, if we start off with 220 as a frequency, a low A just below middle C, and then we go to 440, which is an A above middle C, that's an octave. But if we increased by another 220, which would take us to 660, that wouldn't be another octave higher. We have to multiply by 2, not just add on the same amount. And as I say, that explains the fact that intervals work the same regardless of pitch. So the Western scale divides an octave into 12 intervals, which we call semitones. We all know this. I'll come back right at the end to why we seem to have settled on a scale with 12 notes, or 13 notes if you include the one at the top. And of course, not every culture does use this. There are lots of other scales around, but this has become pretty well universal in Western music. And so one way of categorizing intervals is to say how many semitones they contain. So a major third is 4 semitones, a perfect fourth is 5 semitones, a perfect fifth is 7 semitones, and so on. And some of those, particularly the fifth, will become important in what I've got to say later on. What makes an interval sound nice, and I put that in quotes, to most of our ears is still a little bit of a mystery. I mean, we know what it is, but we don't really know why it is in terms of the, you know, the neurology that's behind that perception. But basically, an interval which corresponds to a rational ratio of the frequencies is something that sounds nice. And what we mean by rational is that it can be represented by 2 whole numbers and usually 2 quite small whole numbers. So we've already seen that an octave has a ratio of 2, a perfect fifth is 3/2, so the top note is 3/2 times the bottom one. So going back to my example earlier, sorry, there's a bit of a sound as though somebody was eating crisps. If somebody is unmuted, could you please mute yourself and then feel free.
Somebody's joined and is unmuted. Lenovo tab M10. You can mute people from your end.
I thought I could, yes, but
Yes.
when I look at the participants,
Yes.
Oh, well, I can't do that without going out of the share. So please check that you are muted, particularly if you are Lenovo tab. Right, I think I have muted you now. Yes, sorry about that, rather invasive action. Right, where was I? Yes, my example earlier on, A440, but if we add on another 220 to get 660, those two notes, that will actually be an E, and those notes will be a fifth apart because the ratio of their frequencies is 3 to 2. And for a perfect fourth, the ratio is 4 to 3, and so on. And again, I'm not going to go back, but you can demonstrate that with the tone generator, you know, to get a practical demonstration of the fact that this is true. But as I say, we don't entirely know why this might sound nice and others don't. There are some possible reasons, which I'll come to in a minute, but it's certainly a fact. So here's a table of the ratios for, I've called it pure intervals, intervals which are perfectly in tune. A unison, obviously 1 to 1, an octave 1 to 2, a fifth 2 to 3, a fourth 3 to 4, and so on. So they're all quite simple rational ratios, and quite a few of them are what a mathematician would represent as n to n plus 1. So 2 to 3, 3 to 4, 4 to 5, 5 to 6. Then they get a bit further apart, but they're still very small, simple numbers. Whoops, gone too far, sorry. And you can see this with, for instance, thinking of the string. I'm sorry to keep citing string instruments, but I am not a blower, so I'm afraid those of you who are can probably translate this to your instruments. But if you just bow an open string, then this is the sort of frequency that you will get, called the first harmonic. If you stop the string, I think the site I pinched this from was about guitars, so these frets are guitar frets. If you stop it halfway along, you'll get something which is an octave higher, and so on. And of course, those of us among us who are players of modern strings know that if you touch the string at those points, you will get high harmonics. That's a feature which is used in musical compositions for violin and cello and so on. This is not new information by any means. Pythagoras is often credited with discovering this. Now, I have to tell you, and I hope this is not going to be equivalent to saying that Santa Claus doesn't exist, but there are now doubts whether Pythagoras was actually a bloke, one identifiable individual. People in the Middle Ages were liable to ascribe things to him, to this named person, but in fact it was probably a whole school of scientists working around the same time. Anyway, here they are. I just love these engravings. Doing a demonstration, you can see that this chap has got bells, which have, presumably these represent the weights, 16, 12, 9, 8, etc. And he's hitting them. He's hitting the 16 and the 8 simultaneously, and I would guess that he's finding that those are an octave apart. This one has filled up a series of identical glasses with, I don't know, water, mead, whatever. Again, they've got the labels, and he's hitting them with little sticks. He's doing 16 and 8 again. This one, it looks a rather grim piece of equipment, but it's actually just strings with weights on the end. And again, he's plucking the 8 and the 16, should be an octave apart. And these guys, because you can only, well, I believe there are things called double flutes, but on the whole, you only blow one at once. So it takes two people, one of them blowing an 8 and one of them blowing a 16. And again, those should be an octave apart. So this has all been known for a very long time. And of course, organists, you know, we talk about 4-foot pitch, 8-foot pitch, 16-foot pitch, sort of related to this kind of theory. Right. This is a very important fact. If we put a fourth on top of a fifth, we get an octave. But if we multiply the ratios of those two intervals, a fifth and a fourth, 3 over 2 times 4 over 3, do a bit of cancelling, that's 2. So in other words, if we multiply the ratios of the two intervals we're stacking up, we get the ratio of the overall interval. And so what that demonstrates is that stacking intervals on top of each other is equivalent to multiplying their ratios. This comes back to what I said earlier, that this whole thing works in a multiplicative sort of way. And although this is not a proof, it is only a demonstration with two ratios, you can fiddle around and you'll find that the same is true for any pair of intervals. So I'm going to say that again because it's so fundamental. Stacking up intervals one on top of the other, we multiply their frequency ratios to get the overall ratio of the resulting interval. So what's the problem? Well, for many instruments, and I'm including the voice as an instrument, violins, etc., making sure that intervals are in tune in the sense that the ratio is perfect, is a nice ratio, isn't really a problem, because a violin can, as we know only too well from beginners, can play absolutely any note. It is not restricted to a series of notes. You might say it's a sort of analog instrument rather than a digital instrument. The voice is the same. I believe, and I'm conscious here that I'm treading on dangerous ground, not being a blower myself, but I think for some wind instruments you can actually bend them. I know this is true because I've worked with Baroque flautists, that you can change the pitch to some degree to make an adjustment. But for keyboards in particular and fretted instruments, adjustment is not really possible. At this point, I know that for viols you can pull the string slightly sideways and change the pitch a bit, and my husband, who's a clavicordist, assures me that on a clavichord, by doing that thing you do with your finger, you can change the pitch a bit, but not nearly as much as you can, you know, with a voice where you can sing absolutely any pitch you like. And so the difficulty is, how are you going to arrange things so that a keyboard sounds nice, in the sense that I've used that word before? So let's look at the equally tempered scale, which is what modern keyboard instruments are certainly tuned to. We want all the semitones to be equal. So what should the ratio be in order to achieve that? Well, let's go back to our fundamental fact. If the ratio is called y, so you might have expected that this being mathematical, there would have been a bit of algebra somewhere along the way. If we call the ratio y, 12 semitones stack up to an octave. And we've got this fact, therefore we multiply the separate ratios to get the overall ratio. So we multiply y by itself 12 times, which in our notation is y to the power 12, and we want that to be equal to 2, the ratio for an octave. So if we solve this little equation, y to the power 12 is 2, and so y is the 12th root of 2. Remember, the number that multiplied by itself 12 times comes to 2. And if you resort to your trusty calculator or Excel or whatever, you find that to as many decimal places as you have facilitated, 1.059463, etc., 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 is the 12th root of 2. It's what we call an irrational number, because that decimal goes on forever and it never repeats itself. More familiar irrational numbers, you might recall, are pi, that's associated with the area and the circumference of a circle. So it's a very, I wouldn't say unpleasant number exactly, but it certainly isn't a nice tidy number, let alone a nice tidy ratio. Oh, just this is an incidental. People who went to school before a certain time, like me, may have been taught to call these things surds, which is a very nice word. So piano tuners want to make all their semitones have that ratio. which is fine. We'll come back in a minute to how they achieve that. But we've already said that frequencies are nice when they are in a simple rational ratio. That means there's no what we call beats. Again, I'll explain that a bit more in a minute. So a pure third has a ratio of 5 to 4, 1.25. But we've just said that a third is 4 semitones. So its ratio will be 1 semitone, the 12th root of 2 to the power 4, and that comes to, with a bit of arithmetic, 1.2599, etc., 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 which is nowhere near 1.25. It doesn't even round off to 1.25. It's too big. So the moral of that is that thirds, major thirds, I should have said major third, in equal temperament are noticeably sharp. The trouble is they're not noticeably sharp to us because those of us who are brought up playing the piano have had our ears kind of corrupted, so we probably don't notice, but it is nevertheless the case. And here's a table with all the equally tempered intervals compared with the perfect ratios. So here's our perfect ratio for a third, 5/4, and instead of being 1.25, we've got this 1.25, etc. These are just rounded off to 5 decimal places. So the percentage error is quite big, over 0.75%. And then in the last column, we've got the errors as numbers of cents. And you can see the same for others. Here's a fifth, which is quite a bit too high, too low rather. It should be 1.5 and it's only 1.498, etc. It's not as much out as the third, but the sixth is even worse. The sixth should be 5 to 3, and in fact, which is 1.66 recurring, etc. In fact, it's this 1.68. It's out by nearly 9%. So sixth, major sixth in equal temperament are very sharp. Now, this only became an issue relatively recently. So, for instance, the very early stuff, Ars Antiqua period, which is absolutely wonderful stuff, but it was nearly all vocal. You know, they might have had a drone from some sort of low buzzy thing, but there were very few thirds. I believe, this may be apocryphal, but I believe there was one of the popes who issued an encyclical saying that certainly music for use in church shouldn't involve thirds because they kind of inflame the lower elements of our nature and are therefore not suitable for religious use. Anyway, so there weren't thirds. So this business of out of tune thirds or how should we tune them or whatever didn't really occur. So at this point, I hope I'm going to play for you a little clip of a bit of Ars Antiqua. This is rather a blast from the past because it's David Munro's consort. But people aren't doing this sort of thing now. Sorry, this is a little side rant. You know, authentic, historically informed performance has come to mean doing Wagner with proper Wagner trumpets. Anyway, just we'll have a little blast of this. And so on. That, you'll be interested to know, was at the setting of the first syllable of the word viderunt. But you can hear that although there are sort of passing thirds in there, they don't matter. The basic structure is fifths and fourths. So it wasn't really a bother. But when people started wanting to use in-between intervals, as it were, then it became more of a question. Okay, let's talk about the circle of fifths, which I'm sure everybody's heard of. That if you go round in steps of a fifth 12 times, we should end up where we started, but 7 octaves higher. So we start from C, G, D, etc. We eventually go through all the notes of the chromatic scale, and we end up back at C. So I did promise you at this point a little digression on the question of beats. I don't know how well you can see what's going on in this picture, but if you've got two notes which are very close together but not identical, then sometimes the sounds will reinforce each other. So where the things are what we call in phase or close to being in phase, they will add up to a louder sound, and then where they are out of phase, they'll cancel each other out, so that this one at the bottom is the sum of those two separate notes. And you can see that we've got a kind of a much slower wave in here, and that's what's perceived as beats. So this explains why sometimes, oh, who shall I offend here? Well, perhaps with school recorder consorts, shall we say, if they're supposed to be playing in unison, you sometimes get a rather unpleasant, almost buzzing feeling in your ears. That's because of the beats. Beats are quite handy. This is what piano tuners use. You know, piano tuners, you don't see them sitting there with their phone and their electronic tuner. They do it all by ear. They are trained to hear the beats and to hear the frequency of beats that they should get when the notes are what I might call sufficiently out of tune or correctly out of tune in equal temperament. And many harpsichordists tune temperaments by beats. You can get tables that tell you what the beats should be for certain temperaments. More about temperament in a minute. So that's the way that beats work. And I'm told that before people knew about acoustics, there were places in concert halls where you could hardly hear anything because the reflections coming from two directions just cancelled each other out. I once heard a fascinating talk by a BBC engineer who explained the best place to stand when you're standing with a wall behind you, depending on what instrument you're playing and so forth, so that the audience gets the optimum effect. It's a very interesting topic, but one for another day. Anyway, there's our circle of fifths. I think something's got a bit out of order here. No, this is all right. So-called Pythagorean tuning is based on having the fourths and fifths perfectly in tune. So 7 octaves, according to our rule, is going to have a ratio of 2 to the power 7, which is 128. But 12 fifths, which should also add up to the same as 7 octaves, the ratio for a fifth is 3/2, and that to the power 12 is this rather lengthy number, which isn't irrational, that it terminates, that's the end, but it sure as heck isn't equal to 128. It's much too big. So yes, the statement of what might be called the bleeding obvious, 128 is not equal to 129 point, etc. So to put it bluntly, 12 pure fifths don't add up to 7 pure octaves. The circle, so-called, is not closed. It's a spiral. And you could go round and round for a very long time, forever, before you'd get back to where you started. This is the fundamental problem. So the difference, the discrepancy between the 7 octaves and the 12 fifths, you may have heard the expression, it's a comma. It's the Pythagorean comma. It's about 1/55th of an octave, or 23 cents, which is really quite perceptible. It's Pythagorean because there are actually other commas. You may have come across the syntonic comma, which is a different one, but there isn't time to go into that today. So what are we going to do about this? Well, either we can spread it out evenly, sort of spread the misery a bit, and that's equal temperament. So nothing's perfect, but everything is pretty well acceptable, for which read not perceptible to most people's ears. Or you can have all the fifths in tune, except one, which is going to be horribly out of tune, because it will have all of that gap in it. It's got to be very much flattened. If we just pop back for a minute, you see that the 12 fifths is too high, so the last of those fifths, as you go round the circle, has to be squashed, and therefore it's flattened. That fifth is called the Pythagorean wolf, and they call it a wolf apparently because it howls, you know, because to the ear it's making a very unpleasant howly noise. Now, if you're going to stay in what I might call fairly unadventurous, that's not fair, but in keys such as C major, G major, F major, etc., which don't use too many accidentals, that's not going to be an issue. But if you want to wander off into A flat, you may find that you're hitting that wolfy interval quite frequently, and it doesn't sound very nice. So for music which didn't wander so far, modulate so far, and you could hear with that that clip of Ars Antiqua that it was basically all on the same chord. It didn't really move around at all. So if you hide the wolf among what we would call the black notes on the piano, that's not actually going to make a huge difference. You won't come across it. You know, the wolf will remain hidden. Or the third possibility is to use a system which will spread the difference out unevenly, and that's what we mean by temperaments, or I suppose, strictly speaking, historical temperaments. So called because we temper some of the intervals to make things work. So, as I've said, equal temperament spreads the comma equally, clues in the name. Mean tone tuning has pure thirds and squashes the fifths. There are actually different mean tones. The one that's encountered most frequently perhaps is quarter comma mean tone, which is a quarter, or 4/3 squashed by a quarter of the syntonic comma, but we won't go there. But different systems do it in different ways. That gives you problems with some of the thirds. So if you have, you know, you can't have your cake and eat it. If you have a G sharp making a nice third with an E, then an A flat will not make a nice third with the C. You can't have both. And as I've said, that's okay as long as you don't wander off into very peculiar keys. There are other systems, some of the most familiar temperaments probably are Velotti. Werkmeister actually had several, but you know, Werkmeister number 2 I think is used a lot. They hide the wolf in different ways. And I'm not going to go through this because frankly it's a bit boring. I mean, it's just saying the same thing only in slightly different ways. Something that interests me particularly as a singer is that composers like Purcell knew this, and they actually made use of the interesting intervals, dodgy intervals, crunchy intervals, whatever you want to call them. Oh, excuse me, I don't know what that phone's doing, but hopefully, yes, my husband has answered it. Yeah, they made use of those intervals to sort of ratchet up the emotional impact, particularly in vocal music. And I think that's one reason why we find that there tends to be a similarity in the keys that Baroque composers choose for particular moods or emotional states. You know, everybody knows that triumphant music tends to be in D major and so forth. Whereas with equal temperament, you just don't get that. Everything is kind of ironed out. So all the fifths on a modern piano are tuned to, I don't know why I've used this Excel symbol for to the power, but it means the same thing, 2 to the power 7/12, which is a bit less than the pure ratio. But at least when we go round the circle, you can shut your eyes if that formula looks a bit alarming, but it's just saying it's 12 fifths. Here's the ratio for 1/5 to the power 12. We get 2 to the power 7, which is the correct ratio. So, phew, the circle of fifths is closed with equal temperament. So here's a little table which compares the different approaches to dealing with this complication. I should say perhaps at this point that there are a lot of what I can only call fruitcakes out there on the internet who have theories about all this. That yes, there really is a way of making everything in tune. It's just that we haven't discovered it yet, you know, and when we discover it, there'll be peace and harmony. It's not true. Mathematically speaking, it's impossible. So we have to take our pick. With equal temperament, we don't get any wolves. The fifths are acceptable. The thirds are pretty sharp, and all the keys really do sound the same. With the Pythagorean tuning, there's one horrible wolf. The fifths are pure, the thirds are very sharp, but again, there are no colour contrasts, there's just a nasty interval. Mean tone has some wolves, the fifths are okay, the thirds are pure, but still not really much in the way of colour contrasts. And then what I've called 18th century temperaments, things like Velotti, there aren't really any wolves. I've said not really because depending on how acute your ear is, there are some slightly nasty things, but they're not, you know, they don't howl in the way that a Pythagorean wolf would. The fifths are acceptable. The thirds vary depending on which temperament you're using, and you might tailor that to the key you're playing in. And there's definitely the opportunity of contrasts of harmonic colour. So, is this the only way? No. People have proposed scales with more than 12 notes. It's a bit of a kind of industry. But we're so accustomed to a 12-note octave that music written in these other scales, to me, it just makes me feel really queasy. And I was going to give you another little clip at this point from the website of a guy who seems to make an industry out of inventing funny scales. Now, where is he? Here he is. So this is a clip in a octave which has 11 steps rather than 12. So it's a very small difference. I think you get the scale first and then you get some chords. Too bad. Also not too bad. And so on. So there's not much difference, but there's enough difference, I think, for things to sound really rather unpleasantly out of tune, not least because there's a horrible vibrato on whatever it is he's using. So we'll we'll get rid of that quickly. Let's have a look at this one. Here we've got the difference between an equally tempered interval and it's called JI, just intonation here, which means what I've been calling pure, perfectly in tune. And they're all sinusoidal, so very pure sounds. So obviously a unison is the same in both cases, but I won't go through the whole of this, but a tone, that's equally tempered, that's absolutely in tune. Let's have a third, which we know is rather sharp in equal. I think that one is really perceptible. The fifth, which was the sixth, which is very sharp, and again that's very noticeable, and so on. So I'll put this on the handout as well, so you can play with it a bit more. But let's get rid of that and go back to here, and I've nearly finished. So I'm going to move on now to the little tailpiece for mathematicians. And if you're of a nervous disposition and not mathematically minded, you might want to shut your eyes at this point. If we go back to our equation, which says that we want A fifths to be exactly equal to B octaves, so 3/2 to the A equals 2 to the B, and we take logs and twiddle things around a bit, we get an equation which says B over A must be equal to log of 3/2 over log 2, which is this decimal. So this is an irrational number. What we're looking for is a rational approximation, which is of the form B over A. So we want, just to say that again, we want A number of fifths to add up to exactly B number of octaves. Now, it's obviously not possible because this is irrational, but by using a strange thing called a continued fraction, which I certainly never learned about in all my mathematical degrees, the only other time I've come across it is when I had to teach mechanical engineering apprentices, would you believe, and it comes into the calculation of gear ratios. Anyway, what it means is 1 over 1 plus 1 over 1 plus 1 plus 2, etc., etc. And we can truncate this at any point. And surprise, surprise, if we stop after the first few terms, we get a scale with 12 steps and 7 in a fifth, which is our old familiar scale. The next approximation is 24 steps in a fifth and 41 in an octave. So tiny little intervals, which really people again have composed music in this system, but it just sounds extremely weird. And as we might say, it would do your head in, I think, to listen. So that's everything I had planned to say. I see I've got 3 minutes left, but if you don't mind going over, I certainly don't. So I'll get rid of this now, stop sharing, and see if we've got some questions. And if you want to ask a question and you want to put your virtual hand up and unmute yourself, feel free. Marilyn, I think.
I thought the sound of my piano for many years was just, it naturally vibrated, but obviously from all you're saying, these are the beats between the notes. So how do you, as a musician that sings and plays string instruments, how do you find a piano?
Well, as I said, I think we get corrupted. You know, piano was my first instrument, and so I am so used to it.
Yes.
that it doesn't really bother me. And if you're doing, you know, if I'm playing a Brahms song for a pupil or something, there's so much going on. And you've got the pedal and you can sort of smear it all out.
Yes.
It's only if you really focus, if I really focus, that I think, oh, I do find with organs sometimes that that's probably because they're not actually very well in tune, or they've got dead mice in the pipes or something.
Thank you.
One of Jenny or Jonathan has a hand up. Yes? Unmute? Was it a mistake?
We've got musical friends, keyboard players in particular, who still swear blind that playing in D flat major sounds completely different from playing in something else, even when they're in equal temperament. And they won't be gainsaid, you know, by all the arguments I can put forward. It's extraordinary.
Yes, I mean, I have a certain amount of sympathy with that. If you're a pianist and you play the opening of Chopin's Funeral March, you know, pom 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 pom, in B flat major, which is the key it's in, and then you play it in B major, it is just not the same. Now, whether it's because we're acculturated to associate B flat major with very miserable music, I don't know. And I don't know what's going on. I think there's a lot more work to be done. You know, if I were younger, I might want to go back and do a PhD on the neurological implications of musical perception, because there's so much we don't really understand.
Yes, that's really interesting.
That's not a very definite answer, I'm afraid, but it's how I feel. Peter.
Hi. Yeah, it's more of a comment than anything, but I often play flute duets with a friend, and if we play a slow piece and we play an interval, say a major third, perfectly in tune, then you get the difference tone, which is the ratio between the two notes that you're playing. And we have one interesting piece that we like playing from time to time, and it's got some quite odd notes that two of us play, but the difference tones, if you listen intently to the difference tones, you actually get the Coventry Carol. They put high intervals in, you know, certain relationships so that the resultant tone that you hear for each interval just spells out this melody. It's quite fascinating to play.
You think it was done deliberately by the composer, or?
It's a deliberate arrangement to do that, yes.
Right, yeah. I mean,
if you want, I'll send you a copy of it. But
well, of course, I haven't said very much about overtones and the harmonic series because, as you can hear, there's a hell of a lot to say. But that's how these people in Central Asia produce the overtone singing, and you know, how they can sing a tune and an accompaniment at the same time. I thought this would be quite fun to try, until I read somewhere that quite a lot of them die while they're doing it because they have to generate such a huge pressure, you know, that they have brain hemorrhages and things. And I thought, no, I don't think I'll go there. Who else have we got? Andy.
Oh, hello, Claire. Thank you very much for a very interesting talk. I play the Hammer Dulcimer, and since taking it up, I've noticed I'm much more sensitive to tuning than when I was playing the flute. In the course of learning this instrument, I get to hear a lot of Iranian music played on the santur, and the thing we've noticed there is that the third and the sixth of the scale are tuned about a quarter tone flat to what we would normally consider in tune. And it's more of a comment really, but it was interesting that in the early part of your discussion, you were pointing out how the third and the sixth tend to be really out in our equal temperament. And it almost makes me wonder if they have just a different approach to dealing with these rogue thirds and sixths, and say, oh, well, let's just flatten the heck out of them and make it our music.
I'm sure they do. Yeah, and other scales just leave them out, or leave out some of the awkward intervals altogether, which is
pentatonic's the ultimate cop out.
Yes, right. Cut the Gordian knot. Sarah.
Hello, Claire. Just really wanted to ask you the kind of practical, what do you choose to tune your harpsichord to? And do you change it if you're playing French music, you know, Rameau, Couperin, Scarlatti, Bach, you know, or,
I am not the person who chooses the harpsichord tuning in this house. I mean, the historic keyboard instruments are my husband's toys. But yes, he does decide. I mean, he will sometimes use mean tone, particularly if he's playing very early stuff. You know, he'll use Velotti perhaps if he's doing Frescobaldi. And I think there is, I don't know much about this, and he's gone to answer the phone, so I can't ask him. But I think, you know, there is some evidence, or people have researched what tunings would have been used for certain composers. Yes.
I've heard that mean tone's better for like the virginals books, the early virginals.
Yes. Yeah.
And you want Velotti rather than equal temperament for Bach, is that right? He wouldn't have had equal temperament as we know it.
No, I mean, it's certainly one of the sort of great lies of the 20th century that the well-tempered clavier is so called because he was so thrilled with equal temperament that he wanted to write something in every key. That's just rubbish. But
you still got the actual key colours then coming through.
Yes, absolutely. Yeah, and I'm sure that's what he wanted. I mean, why did he put the Mass in B minor? Back to Jenny's question, really, about the sort of emotional feel of that key. But yes, I think harpsichordists in general do adjust, and quite often, you know, if you've got a harpsichord CD and you look at the sleeve liner, it will tell you, you know, this was an instrument made by Thingamy, and it's tuned to such and such.
Thank you.
Pat.
Just picking up what Sarah said, I mean, a few years ago, about 2 or 3 years ago, I traded in my dying ancient baby grand for a rather posh Yamaha, which has electronics beyond the hammers. So it's got hammers like a piano, and then it goes on beyond that, which has the great advantage that you can pick different temperaments. And playing Bach 48 on with Werkmeister was quite a revelation.
So it's a proper piano.
It's a piano until you get to the hammers, and then after that it's electronic with
extraordinary
loudspeakers and things. So that means you can adjust the temperament at the press of a switch, basically. And as I said, playing Bach on the 48, yes, okay, it's still a piano, because although it can pretend to be a harpsichord, but it's not a very good sounding harpsichord. But the 48 in Werkmeister was quite a revelation, especially when you get to the more remote keys with lots of flats. It's quite fascinating.
Yeah, Julian Simmons, who I got that name right, who gave us a talk about Handel during the lockdowns. But during the first lockdown, he played one of the 48 every night at 9 o'clock, and we watched it. And it was really nice because it was like a fixed point in that rather weird time. And we noticed that there was such a difference. I can't remember, unfortunately, what tuning he was using, but certainly we'll all have to get one of those pianos, I think.
Take out a mortgage if you haven't got one.
Ah, right. Heather, I think you were waving. You're muted.
I'm not quite sure how to frame this question, really, but it occurs to me that one has to make the assumption that there's a kind of universal standard of how you hear things. But in my mind, I know that as we get older, our hearing deteriorates, but generally speaking, different people, according to their kind of hearing, respond to these different things differently. For example, when you gave the example of the sixth and you being much sharper, and you said you didn't like that. I didn't notice that six was sharper. Now that might be because I'm just too old and my hearing isn't as good, but I'm just interested in whether there's a sort of universal
No,
race theory.
absolutely not. I mean, there seems to be a universal perception of certain things, like an octave is an octave is an octave. You know, whether you live in Outer Mongolia or Scunthorpe, that you will perceive a note that's got twice the frequency as being an octave higher. You may not know the word, but you'll think it's the same note. But beyond that, no, people's acuity varies enormously. Hence that little test website that I mentioned, where you can go and find out what you can distinguish. And in fact, on that website, they ask you questions for the purposes of their citizen science. They ask you questions about your musical experience. You know, what age did you play an instrument? What age did you start? Do you still do it? All that sort of thing, because obviously they're controlling for all those variables when they analyze the data. So it does vary tremendously. I think in my experience, and this is just, you know, from my singing teaching, there are very few people who are really tone deaf. Somebody will come along and say, I'm tone deaf. But all they mean is that they can't sing in tune. And very often that's a matter of coordination. But if you play them, you know, God Save the Queen, and then you play, I don't know, the Marseillaise, they will be able to tell the difference. It's not that they are just hearing a sort of jumble of noise. But it does vary tremendously.
Yes. So does it vary according to one's emotional response to the different sounds, as well as whether you can distinguish, if you can distinguish between them? So what
I don't think I know enough to answer that. I mean, that sounds like a piece of work that hasn't been done yet.
Right.
I know it varies with different cultures and different ethnicities. You know, I don't know if you've ever listened to any Chinese opera, but I personally would not find it a pleasant experience to sit through an evening of that. But obviously, lots of people do, because there's a lot of bending of notes, which to my ear just sounds, I hesitate to say weird, because that's probably not politically correct, but this is a statement about me, not about the music. You see what I mean? It's partly what you're used to and what you're brought up with.
Yes.
And lots of people who don't think, I mean, perfect pitch is another thing we didn't go into, but lots of people who say, oh, it won't make any difference to me if you play this in F and I'm looking at a copy in G. And then they're completely at C. They say, I haven't got perfect pitch, I won't be able to tell. But for various other reasons, like the way it feels in their voice, it does make a difference. So it's very complicated, which makes it so fascinating.
Yeah.
Yeah. Anybody else? Okay, well, I hope that was interesting, useful, whatever.
It was.
As I say, I'll put the whole recording on the website, but probably that won't happen for a few days. And I'll also put some references if you do want to go to those various websites and have a play around. And it's lovely to see everybody, particularly friends outside of SWEB that we don't see very often. So, as people say these days, enjoy the rest of your day.
Yeah.
Thank you very much.
Thank you.
Thank you.
Thank you very much, Claire.
Thank you so much, Claire. That was lovely.
Claire.
Absolutely super. Wasn't
Thank you very much.
Yeah.
Bye all.
Really
Bye.
nice. Thank you so much.
Bye.
Bye all.
Bye.
Bye. Thanks, Claire.